Okay, looking at the 2015 exam paper, just done the mechanics questions onto the waves and optics. So here we have Pete's first question. The superposition of the two waves g of x and t is a sine kx minus omega t, and h of xt equals a2 sine kx plus omega t is a standing wave when. Okay, the standing wave, there's three conditions you need. You need each wave to have the same amplitude, and they need to have the same wavelength, and they need to be moving in opposite directions. Okay, that's a minus omega t for moving to the right and a plus omega t for moving to the left. So you can see from looking that they have the same wavelength. K gives you the wavelength. They have this moving in opposite directions, plus omega and minus omega. So we just need A1 equals A2. So that's that one. Okay, so polarized light. Two sheets of Polaroid are placed above an unpolarized light source. The light intensity transmitted by the Polaroid closest to the light source is I. The second sheet of Polaroid is rotated with respect to the first so that no light is transmitted through the combination. So it's at right angles, okay? A third sheet is inserted between the first two sheets such that its polarization axis is at an angle phi with the Polaroid closest to the light source, where phi is not an integer multiple of pi on 2. The intensity of the light transmitted through the three Polaroid combination is. Okay. Ooh. So we have a light source. It's tricky to draw. We have a light source. Light source. We have our initial Polaroid there. We'll draw its axis of polarization there. And we have another one here further on, which is at right angles to it. And then we put in one in between. So here's the one we put in between. Okay, put one in between, and it is draw a dot there. Its polarization is at phi there, like so. Okay, phi with respect to that. Okay, so in other words, the amount that gets through here is I. The amount that gets through this one is I times cos squared phi, alright, because that's the angle with respect to that. And now this here we're looking at from that angle to here. So we've got that much more angle. So we've got coming in I cos squared phi, and we must multiply that by the cos squared of this angle, which will be 90 minus phi. So that'll be cos squared pi over 2 minus phi. Okay, and we look over here and we see intensity is I cos squared phi cos squared pi on 2 minus phi. So D looks like a good one to me. Just beware that sometimes Pete has been known to say amplitude. If you were thinking amplitude, it would be I cos phi. It would be this one. Okay, so the squared comes because you're talking about intensity, and if it's not squared, if you're just talking about the actual amplitude, then you don't square cos. Right. Okay. A pulsed light source together with a light detector are placed 2 meters above the water surface of a swimming pool. A short pulse of light with wavelength 389.0 nanometers is shone vertically downwards. 2 reflections are observed spaced 87.12 nanoseconds apart. If the refractive index of water at this wavelength is 1.333, find the depth of the pool. So what's happening? What's happening is you have the bottom of the pool, you have the surface of the water, and a pulse of light goes down. Some of it goes down and comes straight up. Some of it goes all the way down, hits the bottom and comes straight up. Okay? And so when we emit a pulse, we get 2 reflections, one off the surface of the water and one from there. And this is the time difference, okay? So, now, so the distance that the light travels is 2 times the depth, okay? That's the distance it travels, there and back, that's the extra distance compared with that. So, therefore the time, we would say normally that, you know, velocity equals distance over time, okay? So in this case, I'm going to say it's 2 times the depth over the time, and the velocity here, well, rearranging this, we'll get 2 times the depth is velocity times time, so the depth is velocity, 2 times velocity times time, and 2 times, now what's the velocity? It's 3 times 10 to the 8th meters per second, speed of light, divided by the refractive index, 1.333, and times the time, 87.12 by 10 to the minus 9. So time for the calculator, 2 times 3 exponent 8 divide 1.333 equals times 87.12 exponent minus 9 equals, and I get 39 point, oh okay, yeah, yep, I've multiplied by 2 here where I should be dividing, shouldn't I? Yeah, so it should be over 2, okay, over 2, 1 over 2 times, yeah. So essentially, here, since I've multiplied by 2, I need to divide by 4 to fix it. So I get 9.80 meters B. Okay. Yep, all good. Alright, so that's the end of waves and optics, and now we're on to break down the classical physics. And here we have figure 1, shows Planck's radiation law, which gives the intensity as a function of wavelength and temperature for a perfect blackbody radiator at 300 degrees Celsius. As the temperature is increased from 300 degrees, the wavelength of the maxima will, okay, so there's a formula for this. Basically it says, find it in the formula sheet, but the wavelength gets shorter as the temperature increases, and there it says lambda max times the T is a constant, right? Or lambda max is equal to a constant, call it K, divided by T. Okay, so the peak of that intensity distribution goes as 1 over T. Okay, looking back at the question, and says the wavelength of the minima will increase in proportional T. No, we said it will decrease in proportion to 1 over T. That one. Okay. Alright. A surface of work function 2.2 electron volts is illuminated with UV light of this wavelength. When a detector is held at this voltage with respect to the surface, a current between the surface and the detector plate is observed. A current will also flow for which one of the following conditions of the plate voltage. Okay, so this is a positive voltage. Provided an electron is emitted, you will get a current. If you want to stop electrons, then you have to have a negative voltage, alright? If you have a strong enough negative voltage, then no electrons will have enough energy to reach the detector, and you won't get a current. So, how much voltage do we need? Well, we need to look at, first of all, how much energy the maximum energy an electron can have? Well, its energy of the photon is equal to HF, alright, and this is hc over lambda, and in this case, going to my formula sheet, because maybe, oh look, we've got h there, so I can do the calculation. I can do 4.136 exponent minus 15, that's the one in electron volts, that's h. So if I multiply that by c over lambda, 3, oh, delete, times 3 exponent 8, divide the wavelength, which is 270 exponent minus 9 brackets equals, I get 4.5955 electron volts, right? So that's the maximum energy that electron can get. 2.2 electron volts is what's needed to get it out of the surface. So I'm going to subtract 2.2 and I'm going to get that 2.395 electron volts is the maximum energy that an electron can have after it's left the surface. So that means a voltage of 2.4 volts minus 2.4 volts will be enough to stop it. Okay? And looking at these, what do we need? We need a voltage that is more positive than that. Okay, so minus 2.2 would do, minus 2.1, anything. So this one says that the voltage has to be bigger than minus 2.4. So I like that one. This one says it's got to be smaller than minus 2.2, and that can't be right. Smaller than minus 3 can't be right. It's got to be in this range. Why? That doesn't make sense. If you have a positive voltage, you'll always get a current. Has to be bigger than minus 5.4. Well, no, that won't work, because from minus 5.4 up to minus 2.4 we'll get nothing. So this one, it's A, minus 2.4. Good. Alright. Monochromatic light strikes a metal surface and electrons are ejected from the metal and their energy measured. If the intensity of light is increased, what will happen to the ejection rate and the maximum energy of the electrons? So the intensity of the light being increased means we're sending more photons. Every single photon still has exactly the same energy, we're just sending more of them. Okay? So therefore, the maximum energy of the photon detected is going to be the same. So it can be that, that, or that. The maximum energy will be the same. But there'll be more of them. So it won't be that, because that says lower. Now this one looks promising. Greater ejection rate, same maximum energy. This one says same ejection rate. Well, no, more photons, more electrons ejected. So B, it is. Okay. So much to remember. Alright. An X-ray beam of wavelength 77 picometers. What's a picometer? I think it's 10 to the minus 15. We'll find it. It's directed along the x-axis in the positive x direction and hits a carbon target. Scattered X-rays are detected at an angle to the x-axis of pi on 2 radians. So in comes our X-ray like that, and out it goes like that. Okay? Won't be the same wavelength, it will have lost a little bit of energy. Okay? And then, now it says, and then off goes an electron, boom, 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 like that. Okay? It says, for each of the scattered X-rays, an electron is produced with a component of momentum in the x direction of. Well, look at the, it comes in, our initial system consists of a stationary electron and incoming thing. The x momentum is all in the photon. The photon then goes off at 90 degrees. So in the x direction, what momentum has it got? Nothing, because it's all at 90 degrees to it. So therefore, the x component of the electron's momentum must be equal to the x component of the initial photon. Okay, so momentum P equals h on lambda, I think. So now I want the other h, I want it in. So, and I'll look up pico while I'm here. So I want h 6.626 exponent minus 34 h divided by the wavelength. Now pico, 10 to the minus 15, as I thought. So going back here, divided by brackets 77 exponent minus 15, close brackets, equals 8.6 by 10 to the minus 21. Okay. But they also 8.6 by 10 to the... Why am I seeing 10 to the minus 24 there? Let's do the calculation again. So h 6.626 exponent minus 34 divide 77 exponent minus 15 equals Okay. Puzzled because there's my number, but that is wrong. I'm going for E, none of the above. Maybe I've made a mistake. Maybe I've missed something. Don't know. I tried. Okay. How much energy is required to excite a deuterium atom? 1 electron, 1 proton and 1 neutron from the ground state to the third excited state. Okay. So, ground state, n equals 1. First excited state, n equals 2. Second excited state, n equals 3. Third excited state, n equals 4. Okay, so we're dealing with the standard hydrogen atom, and En, the nth energy level is given by minus 13.606 over n squared. So, let's see what can't be the answer. Well, no, let's just do it. So, what we have, the energy required to excite a deuterium atom is going to be the energy of the final state, which is the energy of the fourth state, minus the energy of the first state. So that's going to be minus 13.606 over 4 squared minus 13.606 over 1 squared. And I'm just going to stick it in my calculator. I'm going to minus 13.606 divide 4, x squared equals minus brackets minus 113.606 equals, and I get 112.7556 electron volts. That's how much energy is needed. Okay, 12.7556, close enough, that one, go with that. It's not that, that's how much is required to remove an electron completely, to put it in a free state. It's not negative, because you actually have to do work to go from the ground state to the third excited state. This, I presume, without doing the calculation, is what you get, maybe, if you think that n equals 3 is the third excited state. Ground state, first excited, second excited, third excited. None of the above, don't know. Okay. Consider the 1 electron helium ion in the context of the Bohr model. What is the quantum number of the associated excited state which, in a transition to the ground state, results in a photon of energy 52.911 electron volts being emitted? Okay, so going to the formula sheet, ENZ is equal to, okay, when in doubt, look it up. So 13.606 z squared over n squared. 13.606 z squared over n squared. Okay. So first thing to do is just find out what the energy of the ground state is. Okay. So the energy of 1, 2 is equal to minus 13.606, so times 2 squared over 1 squared equals, so minus 113.606 times 2 squared. Okay, minus 54.424 electron volts. So that's 54.424 electron volts drops you down from 0 to the ground state. So one of these is, so what do we need? We don't want to drop quite that far. If we add 52.911 to that, we get, the energy we need is minus 1.513 electron volts. So let's just try, say 6. I like 6, that's what I'm going to go for first. So I'm going to say minus 113.606 times 2x squared divide 6x squared equals 1.5117. It's pretty close. I reckon 6 looks good. 6 it is. I'll just try 5 just to see that, to make sure that 5 is not okay. So minus 13.606 times 2 x squared divide 5 x squared equals minus 2.176. Now clearly that's a lot further away, and obviously each of these other ones will be different, so go with that. Now one I'm not keen on. In the Bohr model of the orbital radius of in the Bohr model, the orbital radius of the electron is predicted to be Rn equals n squared a naught z to the minus 1, and the orbital speed to be Vn equals v naught z n to the minus 1. Oh boy. No, I'm not keen. I want to see if there's a way I can do this by cheating. Okay. So there's the radius. Okay, so just looking at this, we see that the radius that an electron is predicted to orbit at is proportional to n squared and inversely proportional to z. So if you have a more highly charged atom, the radius will be smaller, and if you have n is higher, if it's in a higher quantum state, then the radius will be bigger, and it goes with the square of that. And a naught is presumably what it is for hydrogen, okay, because then n will be 1 and z will be 1. The hydrogen in the ground state will be a naught. Orbital speed is going to be v naught, this is again, it's the hydrogen one, times z, so, and divided by n. So in other words, the orbital speed will be faster as you got a higher atomic number, so yep, naturally stronger attraction, so it whizzes around faster. Inversely proportional to n, yes, as you move to higher it'll slow down. Okay, so the orbital period for is expected to be given by so orbital period will roughly be, it gets bigger with the radius and smaller with the velocity. Okay, so bigger with the radius and smaller with the velocity. Yeah, so it's roughly speaking the radius n squared a naught z to the minus 1 over the velocity v naught z n to the minus 1. So roughly speaking, this is equal to n squared n to the minus 1 on the bottom. That makes n cubed z to the minus 1. That'll be z to the minus 2 with some other bits there. Okay, so I want something that's n cubed z to the minus 2. Oh look, n cubed z to the minus 2. Am I confident? No. Am I putting it in? Yes. Yeah. Because I mean, the distance it travels is proportional to the radius. The time it takes is inversely proportional to the velocity. So I think, yeah, I reckon that's good. Go with that. Okay. I'm dying here. Got to get finished through these two more questions. Okay. An electron of kinetic energy 55 electron volts and mass me will have the same de Broglie wavelength as a proton of mass mp when the proton energy is closest to. Okay, so how does it go? P equals h on lambda. Okay, which we can say, right, yeah, P equals h on lambda. So lambda is equal to h on P. Okay, and yeah, I'm talking about kinetic energy, so maybe I'll write this as mv equals h on lambda. mv equals h on lambda. And now maybe I'll square this. Bear with me. So I'll get m squared v squared equals h squared on lambda squared. And then maybe I'll take a half of it. And then maybe I'll divide by m on both sides. Divide by m. And I'll get, therefore, that the kinetic energy is equal to a half h squared over m lambda squared. Okay? Right. So looking at this, we have 55 electron volts. In the case of the electron, it's h squared over the mass of the electron times the wavelength of the electron squared. And in the case of the proton, that's going to be the same, h squared, lambda squared is going to be the same, but instead of dividing by the mass of the electron, we're going to divide by the mass of the proton, much bigger. So our kinetic energy is now going to be, the original kinetic energy, this is a proton, times the mass of the electron over the mass of the proton. Well, so that's 55 electron volts times mass of electron over mass of proton. I think it's something like 1870. Oh, wrong way around. Okay, delete. Times 1 divide 1870. I'm just making it up. That's 0.0329, 0.03. So 0.03 electron volts. Okay. Right, very last. The potential U of x is defined such that in region 1, x is less than 0, we've got a voltage V. In region 2, we've got a voltage of 0, and this region is 0 to A on 2, and region 3, bigger than A on 2, it's V. V is set to an exceedingly large value, so therefore we have, there we are, where the width of this is A on 2. Okay, and this is voltage V here, and the electron is spectrally trapped. And we all know, let's see, it says extremely large energy in the third excited state. Okay, third excited state. So the ground state for this, it's like a pipe. Pipe that's closed at both ends. That's the ground state. Equals 1. First excited state. N equals 2. Second excited state. N equals 3. Third excited state. N equals 4. Okay, so let's look at the number of wavelengths. So there's one wavelength, two wavelengths, so that's one complete wavelength, two complete, so we've got two wavelengths is equal to A over 2, so therefore the wavelength equals A over 4. Oh, there it is. The energy? We don't care. Why don't we care? Well, because if you got the wavelengths right, the energy doesn't matter. Can you do it? I suppose you can. You can go, what is it? P equals H over lambda. So therefore mv is equal to H over A over 4. Therefore m squared v squared is equal to 16 h squared over a squared. A half mv squared is equal to 8 h squared. Divide by m, so we get kinetic energy is equal to 8 h squared over m a squared. Yeah, it's correct. Okay, but we didn't care. End of that section.